So quite a motley crew here. I see my students here. I see people. I see some people from the lab. Now I'll try to make things relatively simple without many technical details. So this will be more or less a kaleidoscope of things that we do in optics. And the idea of this, let's call it lecture, since it is called lecture, is to show you a few experiments that we do in optics, that we study in optics. And these experiments have been selected in such a way as to allow you to see certain things in optics that might appear rather unusual, and I hope they will appear rather unusual, but each and every experiment that you will see today has a perfectly reasonable explanation depending on how familiar you are with optics. Now, if you are not familiar with optics, or if your acquaintance with optics is not particularly good, don't worry, that's fine. Our job here is not to try to understand everything, but rather to see how things work and what happens if we do this and that. And then perhaps later, those of you who will go to university or will study optics at school may be able to understand. And then you will look back and say, oh, I think I've seen this before. That was rather nice, and now I understand how it works. So let's start. Now, the magic of light. Now, light, the word light may be understood in two different ways. One way to think about light is to think about what the human eye can see. So this part of what we in physics call the electromagnetic spectrum. But we can also think about light in slightly broader terms. And this means we start from X-rays and then go all the way to the far infrared region. But let's keep things a little bit narrower. So let's narrow down this range to things that can be observed with the human eye. So the human eye sees in a relatively narrow range. Now, to keep things, to keep the technical details away, we see everything from red to violet or purple. I don't know the difference between violet and purple. A friend of mine tried to explain to me the difference, but it was too complicated for me. She's an artist, I'm not. And as far as I'm concerned, violet, purple mean more or less the same. There's also magenta, but I don't know what this is. Anyway, so from red to violet, from red to purple, this is what we mean when we usually say optics. In principle, we can extend this region, and it will also be optics. So now, let's start with the simple experiment where we have a laser pointer. So where's our laser pointer? Okay, here it is. Now, this is a laser pointer that you can purchase in any it works. Okay, in any shop, I think. And so if I shine light, you see a green spot over there. Now, but you do not see the light ray itself. And the reason you do not see it is that the air in this room is reasonably clear. There are only molecules of hydrogen, oxygen, helium, and nitrogen, whatever. But we can see that bright spot there. Now, we can see it because when light strikes this white screen, it is reflected and it goes into the human eye. And the human eye is a relatively simple instrument from the point of view of optics, but then if we add biology, things become a little bit more complicated. So the human eye gets these rays, so these rays, reflected rays, get into the human eye, and then the lens of the human eye focuses light on the retina. And then we have various things on the retina, various cells, that allow us to see this as green. Now, I see it as green because everything seems to be all right with my eyes. But the thing about the human eye is that there are three types of cells that are responsible for our ability to see blue, red, and green. And then it turns out that if we mix blue, red, and green, the human eye will see white light. And if something is not working properly in the human eye, we have a bit of a problem telling the difference between various colors. And the person who was the first to describe it was John Dalton. So, and in his will, he asked his friend to take out his eyeball and dissect it and see what was going on. So he thought that there was something wrong with his eye, but at that time, at that level of the human understanding of biology, it was rather difficult to understand what was wrong. But now we understand that something was wrong with certain cells in the retina. So now let's see what happens if we shine this beam of light through this tank filled with water. Now, this is not usual water. We have a little bit of sugar syrup there. Now, this is regular sugar that you use in the kitchen and add to your tea or coffee to make it sweeter. Let's see what happens if we shine light through this tank, and then we'll see if we can understand what is going on. So now you see a perfectly straight beam of light, and this is what I was talking about. You see the light itself, because there are a little bit of particles in this water. It's not 100% clear, and light is reflected by these particles into your eyes, and therefore you can see a nice straight line. Now let's lower this beam of light and see what will happen. Oh, now it bends. So the lower it gets, the more the bending is. It is no longer a straight line, but it is a curve. And the reason it happens is that our sugar syrup is not all over the place, roughly speaking. So in other words, the amount of sugar differs as we go down to the bottom of this tank. The amount of sugar syrup increases. Now, why is this so? Well, because the sugar syrup is heavier, in simple words. But the boundary between the sugar syrup and water is not well defined. So, in other words, the amount of sugar decreases as we go up, up, up. So the property of this water changes. And using a little bit of technicalities, we should say that as we go up, the density goes down. Or if we go down, the density will go up. And this is the reason why this light gets bent. So it is no longer a straight line, it is a bent line. And this is exactly the reason why you can see the sun, the setting sun, even though it is already below the horizon. Because the sun, you can't see the sun, the earth is round, and the sun is over there, you can't directly see it. But the density of air changes as you go up and up. And the sun rays go in such a way that they're bent, and you can see the sun behind the horizon, below the horizon, even though it is below the horizon. Now, there is one other phenomenon that you may come across if you travel in a car along a straight road and it is hot. So what happens? The road is black, and we all know that in the summer the asphalt gets rather hot. So hot that it sometimes melts, and a heavy lorry can leave tracks if it travels down this road. Now, this hot asphalt hits the air, and it causes the density of air change. Now, this means that we have a different amount of air particles as we go higher and higher. So this creates a similar effect to the one that we have here. And therefore, you may think that there is a puddle way ahead. Now, you see the puddle because you see the reflection of the sun in the puddle. You think there's water. But this is not actually the case. What happens is the sun is over there, and the ray of the sun goes down, but then it is bent and it goes into the human eye. But the human eye, the human brain, thinks that light only travels in a straight line. So we think that we're looking at the reflection of the sun in that mirror that is created by the puddle or the pond or whatever it is that contains water. So this is called a mirage, and this is can be observed in deserts as well. But as you get closer to what you think is a reservoir of water, you discover that there is no water there, only this straight road, and there is nothing else. And you are lucky if you have a couple of bottles of water to keep you going. So, now what happens as you get closer to what you think is water, the angles at which the light rays go to your eye change, and this mirage disappears. So this is the reason. Right, now let's have a look at another experiment and try to understand what's going on. Let's take our laser pointer and now shine light at a slight angle to the boundary that separates water from air. Now you see a nice reflected light. So this ray is broken because there is a discontinuity. Now, if we increase the angle slightly, if we change the angle, then we should be able to see something else. Can we see it? Can we see that bright spot? You might want to start at the bottom and at a slightly greater angle. Okay. No. Let's do it here. Okay. Now, you see first of all that bright spot. And at the same time, you see that this ray is broken and it gets reflected off the interface of the water surface and goes back into the bottom of this tank. But you also see one more ray. Well, you can't see the ray itself, but you can see the bright spot. This is exactly the same what you saw at the beginning of this lecture. So this ray gets partially reflected off the water surface, and some portion of it goes out of the water and strikes the wall, and you see the scattered light. Now, if we increase the angle, if we change the angle, you can no longer see the bright spot. We only have so we change the angle again. So you can only see the reflected ray. Now, this is called total internal reflection. So what happens is water is more dense than air. It is heavier, in other words. So if you shine light standing at the bottom of this tank, it strikes the surface, and then there is a particular angle beyond which there is no light coming out. So now, how can you see it where can you come across this in life? Now, those of you who do diving can easily observe it. So if you are standing at the bottom of the sea, let's say, not at the very bottom, 11,000 kilometers, I hope, but at the bottom of a reasonably deep tank, you actually cannot see everything that is outside. You can only see what is going on in a small cone above your head. And this is precisely the reason why this is so. Because not all the rays that get into the water or can be detected by the eye, because light goes in a uniform medium in a straight line. So in other words, this ray goes, strikes the water surface, then is reflected, and then part of it goes out if the angle is less than a certain value. And this is precisely what the human can see if he is standing here. So you can only see in a certain cone. Right, now let's move on. So what's next? Now let's stay with this tank for a while and see if we can do something else. Mm-hmm. Okay. Now here's something. We have a light source here, and it goes through a reservoir of water. Now there's a hole here. If I close it, you will not see anything, but there's a hole that allows this light to go through it, and you see a bright spot on that white screen. And now let's open this tank and observe that there is no bright spot on the wall, but this water is now shining. And if you look into this bucket, well, I can see it. This bucket is now illuminated. So what happens is, although the light prefers to travel in a straight line, it now goes along this bent line of water. These two effects are closely related. And what we have here is what happens in fibers. Now, I'm sure that you have all seen those lamps, those decorative lamps, where you have a bunch of plastic things sticking out, and if you switch this lamp on, they will be colored. They will produce light, so you'll see a shining bunch of these fibers. Now this is also fiber, and what is going on here is that, just as in the case of this tank, the density of water is greater than the density of air. The light ray strikes the boundary separating the water from the air in this room, and the angle is such that the light cannot escape out. So it has to travel down this channel provided by the water, and that's why you cannot see anything on the opposite wall, and you see this water channel is shining because there is light bouncing off its walls, but it cannot escape, so you can only see a little bit of scattered light. Now, let's see what happens if we shine light through this aquarium again. So the light will be provided by this projector, but we add a little bit of things. Well, whatever this is, this solution creates a little bit of opacity in water. So we add a little bit of extra particles, but not too many. So if we mix it and now shine a light through this tank. Right. Now, let's see what happens. Now, if I hold a screen here, have we got a screen? Yes, lovely. So if we hold a screen, well, the effect is rather weak, but you can see a little bit of redness here. Well, ideally, this is a very delicate experiment, as are all experiments in optics. Ideally, if you make sure that the amount of this solution is correct, then what you will see if you look at this tank from where you are, you will see it bluish. And here on the screen, as the light passes through this tank, you will see a reddish spot. Now, you can see it more or less every day. On a clear day, of course. The sky is blue. Now, why is it blue? The sun appears yellow, but why is the sky blue? Is there something blue with a blue light bulb or a blue star? There must be quite a lot of stars there to make it blue. No, there's only our sun. So what happens is the sun shines light through the molecules up there, and these molecules scatter light. So the sunlight goes through these molecules either in a straight line, but it may not be a straight line. But the point is, we are here looking at this scattered light, and this scattered light is blue because what happens is that the closer you get to the blue part of the visible region, the greater the scattering. So, in other words, if you shine blue light through air, then a great portion of it will go into the human eye, although the light ray goes past you and it cannot get directly into your eye. So what we see is that these particles redistribute light and it goes into our eye at 90 degrees to the direction of the light ray. So the light ray goes this way, but it goes through air and we see scattered light. It goes into the eye and it is blue. Now, if we shine red light, we will not have a similar effect. The amount of light that gets into the eye will be smaller. So, if we shine white light, and we'll see in a minute that white light is actually not white. It is a mixture of a panoply of colors that go from blue to red, or from red to blue, depending on where you start. So, this white light is scattered differently. And the blue portion of this light, the blue component of this light, gets into the human eye, and that's why the sky appears blue. But in the evening or in the morning, you can observe that the sun is red. Why is it red? It is supposed to be yellow. When it is high above the horizon, it is yellow. It is yellow because it shines directly into the human eye. Of course, you might ask, why is it yellow in the first place? Well, it is yellow because it is sufficiently hot. And we know that if we stick an iron poker into a fireplace, it will get red. It is not because there is a light bulb somewhere appearing in that poker, but because it gets hotter and hotter. And the hotter it gets, the redder it gets. If you keep heating it, this red will turn into orange and then yellow. If you heat it more, it will turn blue. But that's a different story. This is not exactly optics. So the sun is yellow because it is sufficiently hot. And when it is high above the horizon, it is yellow. But as it goes down, the amount of air that the light goes through increases. And all the components of this white light, or let's say more or less white light, are scattered away from us, and they do not get into the human eye. And what is left is red. So therefore, the lower the sun is, the redder it appears. So it is still yellow, but it appears red because there's only the red component of this white light reaching the human eye. And there are various, it will appear more or less red depending on the condition of the air, and some people say that depending on how red it is, you can tell what the weather will be tomorrow. I'm not sure it works. You can just check the weather forecast and it tells you what the weather will be tomorrow. And of course the weather forecast may not be correct either, so you will know what the weather will be like tomorrow when you wake up tomorrow and look out of the window. Right. Now, let's see what is else on the menu. Now let's stick to our white light and see that it is indeed made up of a few components. So let's see what's going on. We have an apparatus here. So this there's a light bulb there that produces white light, and you can see a bright white segment appearing on the wall. So there's a slit somewhere in this apparatus that only passes light in a narrow slit, through a narrow slit. Now let's see what happens if we add something else. Now we see a little bit of this bright whitish slit on the screen. But we also see all the colors that I've just mentioned, from blue to purple, to red. So it starts with actually, well, you can see it from blue to red, but if you are a little bit careful, if your eyes are slightly better than mine, I'm sure you will be able to see purple as well. Now, what is it that we have introduced? Now, this is what is called in optics a diffraction grating. Now, diffraction grating, that's a very clever phrase, but what it amounts to is this. You take a piece of glass and you cover it with black paint, for example, or better still, to make it really black, you cover it with soot, carbon, pure carbon. And then you take a razor, an ordinary razor, and very carefully, this is what people did in the past, in the time of Thomas Young. They were very good at that. So you take a razor and you make tiny slits in this black paint. And you make sure that these slits are very close together. So the closer they are, the better the effect will be. So when you shine light on this diffraction grating, its components are separated. This white light gets split into all of its components, from red to blue. So depending on the color, the bending of the rays that pass through the diffraction grating changes. So initially, we could only see one bright slit. The light goes in a straight line and hits the screen. But there are the components are off-center, and they're off-center because light is bent when it passes through the diffraction grating. And its bending depends on the color. So this simple tool, it is simple conceptually, but it is difficult technically because a good diffraction grating is rather difficult to fabricate, allows us to see that white light is not actually white. It is a mixture of all these colors. And this is not the first experiment where this was discovered. The first person to understand, to discover that white light is not actually white, that it is a mixture of all these colors, that there is a whole panoply of colors mixed together in white light, was Newton. Now, we cannot unfortunately reproduce Newton's experiment. How he did? Well, he wasn't called Newton for nothing. So what he did was this: in a totally black room with black curtains blocking every light, he had a prism. A prism is a piece of glass that is cut in a particular shape. And he made a hole in one of the curtains to get a sunbeam entering his room, shining on this prism. And what he discovered on the screen that he put behind this prism was a lovely spectrum going from red to purple. So that was the first experiment that showed that white light is not actually white, but it is a mixture of various colors. This experiment is much easier to show in our laboratory. But the idea is the same. Certain technical details are different. Why the diffraction grating works in this way is a matter of technical details, and we cannot discuss them here. Likewise, Newton's experiment, conceptually different, but we cannot at this stage discuss what is going on. Right, let's move on. Let's stay with diffraction and see another experiment. So in this experiment, we have a laser, a red laser. So there's only one color, one component. Now we shine this laser through a piece of glass, and you can see a straight line, a nice straight line. This is in accordance with what we expect from light. And now let's move in a diffraction grating, and you see that this straight line is now broken into components, into several beams. They're all still red because there's only one component. A laser produces light of only one fixed color. So this is green, and therefore all these beams are green. But one other property of this diffraction grating is that it can actually bend light in several directions. Right. Now, you may have never done optics. You may never do optics in your life, but you certainly have seen shadows. So if you block light, you will see a nice shadow of the object that is blocking light. And there's a sharp boundary separating the illuminated region from the shaded region. The question is this boundary really sharp? Is it a geometrical boundary like a straight line or a curved line depending on the shape of the object that is in the light's way? Well, the answer is no. We have a beam of red light produced by this laser, and it passes very close to the edge of a razor. This is an ordinary razor that you can buy in any beauty shop. And what we expect naively is a sharp boundary created by the razor's edge. But if we look closer through this camera, now there is no cheating introduced by this camera. If I look at this screen here, I will see what you will see there on the screen in front of you. So if we move the razor into the beam, I can see, and I'm sure some of you who are sitting close, you will see that the boundary is not actually sharp. You see these bright and black strips. And this is exactly what happens if you shine light past an object so that the object blocks light partially. You see what is called the diffraction effect. Right. Now, what does it tell us? It tells us that light does not actually always travel in a straight line. Well, what this experiment reveals is what we call in optics, and what people realized back then when Thomas Young made his famous experiment, that light is a wave. And if it is a wave, it can bend. It can go around obstacles. And, well, what is a wave? The simplest way to visualize a wave is to drop a stone into a pond. And we will see these disturbances spreading from the spot where you've dropped the stone. These are waves. The waves are produced in the ocean, and they enter the harbor. Now, if the entrance of the harbor is sufficiently narrow, what does it mean sufficiently narrow? The waves on the water are a sequence of crests and troughs. So if the entrance of the harbor is comparable to the distance between the crests and the troughs in the wave will actually spread out as it will get into the harbor. But if you open the gates wide, so wide that the entrance is much wider than the separation of the crests, the wave, as it gets into the harbor, will not be spread beyond the gates. So this is the phenomenon of diffraction. We can see it not only in optics, although we tend to think of diffraction as something that is only about optics, but it is actually the general property of waves. And in optics, we can visualize it in a very beautiful way. We have many, many experiments. Now, let's move on with our experiments that have to do with the wave properties of light. So, and one other demonstration that we are going to see in a minute is named after Newton. As you may know, as some of you may know, Newton made a lot of contributions to various branches of physics. But his main contributions were in mechanics, and you all know, well, some of you, not all, I think, but some of you know Newton's laws. But Newton also made certain discoveries in optics, and we've already mentioned one, namely that white light is not actually white. Now, what we see in this experiment is the light produced by this projector gets reflected off a sandwich of two pieces of glass. But they are not exactly flat. They are not 100% flat. There is a bit of irregularity. So they touch at some points, but not at every point. So what Newton actually did in his experiment was he took a piece of glass like this, so it is flat on one side and spherical on the other. This is a lens. And he put it on another piece of glass, a flat piece of glass, and shone light from the top. And what he observed were a series of red and dark and light bands. So this is what we see here. As we jam this sandwich in a different way, we see this beautiful pattern of bright and dark circles. But you can also see that the color changes as you move away from the center. Now, this is because we have a source of white light. So in this experiment, we also can observe that white light is not actually white. Its different components are bent differently by this sandwich. And so we can see this lovely multicolored pattern. Right. Now, what's next on the menu? Those of you who do photography, and a friend of mine is taking photographs here now. Now, if you look at the lens of your camera, and I'm sure that all of you have telephones that allow you to take photographs, you will see that the lens is not white, that it is either reddish or bluish. Why is that? And in the manual, for example, of a very expensive camera, the manufacturer tells you, please do not touch the lens. Well, some of you will say, well, why bother? I touch the lens, there will be my fingerprints, I'll take a clean cloth and wipe it. Well, if you wipe it, you'll ruin the lens. Now, this bluish thing or reddish thing is there for a reason. As light gets into the camera, it produces an image on the film or on the matrix, on the light-sensitive matrix, if it is a digital camera. Now, if you are a photographer, you know that it is difficult to take photographs when it is dark, because there isn't enough light coming into the camera and illuminating that light-sensitive either film or matrix. So you want as much light entering into the camera as possible. we know that some light, some portion of light will be reflected off the lens, as we've seen in this experiment, so in the simple experiment with the tank. Some portion of light gets reflected. We don't want it to get reflected because we want all the light to get into the camera. So the manufacturer takes a glass lens and covers it with what is known as anti-reflection coating. So this is a very thin film that makes sure that as little light is reflected off back to the image and as much light gets into the camera and is projected onto the matrix or the light-sensitive film. So here we have one such lens. If we shine light on it and look at the light that passes through, you see that it is bluish, and the reflected light is reddish. So this is precisely because there is an anti-reflection coating on this piece of glass. As we shine white light onto this piece of glass, the red component is reflected off onto the screen, and what is left is the blue component. And if we look at this lens, we'll be able to see that the surface is slightly reddish, and this is that reddish coating that we see on the lenses of our cameras. Depending on the manufacturer, it may be bluish or reddish. It will actually be some kind of mixture of blue and red, so it will be more or less purple or something like that. But please do not touch it and do not wipe your lenses. So just make sure they're clean. Right. Now, let's do this. Let's take these two objects. So we have two identical pieces of glass here. They're identical. Now, you can see that they are a little bit dark, but this is for a reason that we'll discover in a minute. So if we put one such piece of glass on top of this overhead projector, we see a bright spot on the screen. Now, if we take the second one and allow this light to pass through these pieces of plastic, then cover it with the second one, with the second glass, you see that these pieces of plastic behave in a very unusual way. If we rotate the second piece, you see that the image changes. The colors start to move. Now, what is special about these two pieces of glass? Now, let's remove this plastic and just cover let's make a sandwich of these two pieces of glass, pieces of special glass, and rotate them with respect to each other. It's now dark. And if we rotate further, we go from light to darkness. However, if we only rotate one of them and keep the other away, so let's just play with one. If we play with one, if we rotate just one such piece of glass, nothing happens. So what is it? What is going on? Let's see. Well, we cannot understand all the details, but these two slabs of glass are called polarizers. And I'm sure you are familiar with the word polarizer, or a word that sounds similar. You go to a shop and buy a pair of sunglasses, and the manufacturer tells you that these are Polaroid glasses. They are made of this kind of material. So what happens when light passes through your Polaroid sunglasses is it becomes, it goes into a special state. This state is such that, first of all, not all the light that goes through your sunglasses gets into the human eye. We can show that it is actually half the light. Now, if you, and this is what you can do at home, take such spectacles, such Polaroid spectacles, switch on your laptop and try to look at the screen of your laptop through these glasses, and try now rotating these glasses. You will see that at some angle you will not be able to see through. Why is that? Now here we have two such special slabs, such Polaroids, and if we rotate them with respect to each other and adjust the angle appropriately, no light will pass through. Now, what happens with your laptop is that the light that it produces is polarized. It is prepared in a special state so that you can only see it through your Polaroid sunglasses if your sunglasses are oriented in a special way with respect to the screen. And this is exactly what we have here. When light passes through one Polaroid, it gets prepared in a special state. And this state is such that now this polarized light will get through the second Polaroid only if the two Polaroids are oriented in a special way. So this way, no light passes through. And if I turn the Polaroids through 90 degrees, there's light. Now, when I put those pieces of plastic on the first Polaroid, light goes through them. And you see them, they appear white because they are transparent. But if we make now a sandwich of two Polaroids with plastic between them, we see that the colors change. So this specially prepared light, prepared by the first Polaroid, passes through this plastic. And this plastic does something else to light, so that we can see the effect if we add the second Polaroid. Now, the colors that you can see on the screen depend on something. What is it? Well, if you take a piece of plastic like this, you can see that it is transparent, absolutely transparent. But there is something else about this piece of plastic that cannot be seen by the naked human eye. Imagine that you are sitting in this huge cube of plastic. And you can go and you can look in different directions, or you can just walk in different directions. You will see that the properties are different. Now, if the properties are different in different directions, we speak about an isotropy. So when this plastic is manufactured, it is made of fibers. It is not, they are long and thin, and they are arranged in a special way. And this arrangement creates the difference of properties in different directions. Now, when we shine polarized light through this piece of plastic and pass this polarized light through a second Polaroid, we can see the effect of this difference of properties in different directions. One other thing about this piece of plastic is that it may be twisted in a different way, and depending on how it is twisted, you see different effects only in polarized light. So if we shine this piece of this polarized light through, for example, a cut glass vase that you have at home, and then add another Polaroid and shine this light on the screen, you will see exactly the same effects. Because when this cut glass vase is produced, it is shaped in a particular way. And the shaping creates certain tensions within this piece of glass, and the properties change depending on in the direction in which you are going. And this can be seen in polarized light, only in polarized light. And this is what is used by manufacturers to determine whether this cut glass vase is of good quality or not. So if these tensions and strains are distributed in the right way. Okay, let's do one last experiment. Here we have a column of water, but it is not pure water. We have added sugar to it, and the sugar syrup is very strong. We have lots of sugar that is dissolved in this column of water. Now, if we shine light through this column of sugar, nothing unusual can be observed, but if you look at the ceiling, you see that the spot is reddish. And this brings us back to the experiment that we saw at the beginning of this class. And this is what happens when the sun rays go through air. We can see that the sun is reddish, and this is what we have here, a similar effect. Right. Now let's add a Polaroid. So now light is prepared in a special way, and you see a beautiful pattern of all these colors that we have already mentioned in our lecture, going from red to blue, and then we have green and yellow, etc., etc. So now, if we rotate this Polaroid, you will see that this pattern starts to rotate as well. Now, I look at this column right here, at this spot. I see that this spot is purple. But those of you who sit over there and look at this spot from here will see that it is yellowish. So, depending on where you are, you see a different pattern. But the point is that when polarized light passes through this column of sugar, something else happens. So this column of sugar seems to twist light in some way. And actually, this is what it does. It twists it. So now this polarized light becomes twisted in such a way that the preferred orientation created by this Polaroid is twisted as light passes through this column of sugar. Right. So this is our last experiment. So if you have any questions, please, you are quite welcome to ask them. I'll try to answer them. Right. So there seem to be no questions. And now I would like to invite the head of our Department of Physics to say a few words. Okay, take the floor.